Okay, so let's move on. So we've got light and energy. Light has a particle nature to it. It's both particle and wave nature. Now, those of you that speak French, I apologize. I'm going to totally butcher de Broglie's name. He's French, so it's de Broglie, or however the French might pronounce that. I say de Broglie, which a lot of people do. But he came along and he thought in 1924, after all of these quanta and duality ideas came out, he decided he was going to come up with an idea that if light has particle nature, then why doesn't matter have a wave nature? And he came up with this, and of course, when he first came up with this, he was just like the laughing stock of the science community. It was totally ridiculous. And but then people started doing experiments and it started to explain a lot of things that they saw. So he has the equation that the de Broglie wavelength, the wavelength of a particle, is equal to Planck's constant over its momentum. And if you remember, momentum is mass times velocity. Okay. So that is basically what he came up with, and subsequently he's been proven right that this is the case, that this is what happens. Okay, so let me do a problem here. Yeah, we're not going into a whole lot of explanation here, a lot of his experiments and things, because we're getting into the realm of calculus, which we don't do in IB. So just take it for granted that this is the equation and you can apply it. All right, so we've got an electron that is accelerated from rest through a potential difference of 100 volts. What is its expected de Broglie wavelength? All right, so we've got several things that are going on here. First of all, we need to find out what its velocity is, so we can use this equation. We know the mass of an electron, but we know the energy that there's given, because it's given to us in volts, and we can figure out the wavelength. So we're going to be using the equation, and so basically that's going to be lambda equals E times the mass times the volume. Is that right? Did I do that right? Lambda equals mass times the volume. I'm looking at my notes again. And is that right? H. Yo, sorry. Holy moly. It has been a long thing. This presentation has not wanted to get produced. It's been one technical error after another, so I'm just a little bit off, so sorry about that. Okay, so we have the wavelength equals h over p, which is h over mv. So this is the one that we're going to use because we know the mass of the electron, we're given the energy, so we can figure out its velocity. Okay, so how do we do that? Velocity, kinetic energy we'll figure out the kinetic energy first. Kinetic energy is the charge of an electron times the voltage that it's going through. So it's 1.6 times 10 to the minus 19th coulombs times 100 volts, and that gives us 1.6 times 10 to the minus 17th joules. Okay, so now that we have the kinetic energy equals 1/2 mv squared, and we can solve this to find the velocity is equal to the square root of 2 times the kinetic energy divided by the mass. Make sure I set that up right. Make sure I'm not making another mistake. Yeah, okay, so that looks good. So velocity equals the square root of 2 times 1.6 times 10 to the minus 17th divided by the mass of electron, 9.110 times 10 to the minus 31. Take the square root of that, and we get a velocity of 5.9 times 10 to the 6 meters per second. Now we can take this and substitute it in right there, and so the wavelength is equal to 6.63 times 10 to the minus 34th joule seconds, Planck's constant, times 9.110 times 10 to the minus 34th times 5.9 times 10 to the 6th, and that gives us a de Broglie wavelength of 1.2 times 10 to the minus 10th meters. And 10 to the minus 10th meters is basically an atom. That's an atomic radii. Atomic radius. That's basically the size of an atom. So the wave of the wave nature of an electron makes it is the wavelength size of an electron. I'm sorry, of an atom. Okay, so that's kind of interesting. Such a tiny object has such a huge wavelength compared to its size. Thousands, millions. Let's see, an order of. I'm trying to think of diameter. It's large. It's a lot of zeros. Times the size of an electron is its wave nature. So if an electron has such a large wave nature, such a large size, we're particles too. We're just one great big particle, right? In a sense, we've got lots of little particles, but they all add up. So what kind do we exhibit wave nature as well? Well, let's take a look at that. Let me take a look at two things. I'm gonna talk about me. Me at going 35 miles per hour, which is actually 15.6 meters per second, and I weigh about 205 pounds. So let's see, that's my velocity. My mass is 205 pounds, which is about 93 kilograms. So let's also do me going at as fast as that electron was coming off of the what our last problem. It's wave nature. An electron that had that much energy was moving at that velocity. If I was moving at this velocity, which is pretty close to, it's about 0.2% of the speed of light, which is pretty fast. That's pretty fast. That's really moving. So let's see if I have any wave nature at these. So we're basically using lambda equals h over mv. So in my case, 6.63 times 10 to the minus 34th, 93 kilograms, times my velocity is 15.6 meters per second. And so my wavelength, my de Broglie wavelength is 4.57 times 10 to the minus 37th meters. I'm smaller than an electron. My wave nature is smaller than an electron. The wave that I'm putting out, the probability that I exist within this space is pretty certain, because I'm way bigger than that space. But the faster I go, the bigger my wave should be, right? The bigger my de Broglie wave should be. So let's see what it is. Lambda equals 6.63 times 10 to the minus 34th. I'm still 93 kilograms. Now, honestly, my mass would be bigger if I was going a significant portion of the speed of light. That's just the way it is. But we'll go with, it's still 93 kilograms. And I'm going 5.9 times 10 to the 6 meters per second. And so my wavelength is 1.21 times 10 to the minus 42. The reason why this is so much smaller is because we'll talk about this next time when we talk about Heisenberg's uncertainty principle, but I'm moving, and so it's harder to tell where I'm at. And so my wave function is way bigger, or I'm sorry, way smaller than this one, because it's harder to figure out. No, actually, I'm saying that backwards. My wave is smaller, so there's even more chance of, this is why you see me all the time. No matter what velocity I'm moving, you'll see me moving. You'll see where I'm at. You can see where I'm at because my wave function isn't very big at all. As a matter of fact, it's, I think mathematically, the term for this size of a wave function is zero. It's virtually zero. Even at an atomic level, this would be an atomic level to that one. Again, on much smaller. If an atom's order is minus 10th, if my wave function is on the order of minus 42 or even minus 37th, I mean, even an atom couldn't see me, couldn't see my wave function. It would just be too small. Okay, so next time we will move on and talk about some other ways that matter interacts with radiation, basically the quanta nature of matter, and there will be some intense equation derivations coming out of that. Good news is some of them you're not going to be expected to do. Other ones you are going to be expected to know, but it's algebra, right? It's not, sorry for those of you that really want it to be calculus, it's not. It's algebra 2, maybe even just algebra 1. And the one thing you can look in the book, there is one that there is a calculus derivation for, and they put it in a big box. You're not expected to know how to do this in IB, so they're just showing you how they derived it, but you're just supposed to know the end result of it. So we'll talk about that then. Work on the worksheet up until, let's see, work your worksheet through question number 7 is all. We just went through question number 7. And then we'll talk about what you need to know for 8 through 21 next time. Let's see you then.